Speaker today, our second speaker today is Dr. Nhan from the BAS Center for Applied Mathematics. We will talk on moderately discontinuous homology and Lipschitz normal embeddings. So, please.
So, thank you very much for the invitation. So, and good morning from Spain, because I'm in Spain now. So, today I'm going to present some small counterexample actually for a conjecture in the paper on moderately discontinuous homology. The paper I just draw in the screen, because my talk is quite short, so I decided to take notes instead of present the slide. So the moderate discontinuous homologies is a new theory. This was developed by Bobadilla and his group, and the papers recently published in the journal Communication in Views in Applied Mathematics. Is very new, and because it's new, so I should get you understand the definition first. And my content of my talk includes first I will try to get you understand the definition what is really a moderate continuous homologies and what is used about. And the second is the conjecture and the counterexample. And the third one, I will give some remarks on this. So let me start with the definition. So first is the setting. Oh, sorry. So the setting, I take a term of the subanalytics. This is in or n. So this is subanalytics. Matrix term. This means X is subanalytics and dx is a matrix on X. So given, if you are not familiar with subanalytic, you just consider X as a semi-algebraic term. So given an F from two terms, Y0. So this is a subanalytics continuous. So F is called linearly vertex approaching. If we have the fx minus y0 is preserved in the sense of Lipschitz, x minus x0 bigger than 1 over k, x minus x0. And there is in the case bigger than equal 1. It looks like by Lipschitz map, but only preserve the distance to the vertex. So now I start defining the MD homology. The homology. What mean MD homology? So the MD homology is used to capture the singular homology of the link of the germ after collapsing it with certain speed. So the usual homology is just only capture the homology, right? But now we work with Lipschitz geometries. I mean, we have some collapsing in certain speed. So how to define it? So actually the definition is just mimic the definition of a singular homology. So to define the homology first, we need some notion of a simplex. So let me take some notation. We have delta n is a standard simplex in order n, and because I want to capture the homology of the link, so I have to denote another notion. This is the delta hat. This is the cone over delta n 0, 1. So x belong to delta n. So it look like if you have delta n like this is delta n. So delta n hat is, I take delta n as a length of the cone. So this is delta n hat. Okay. So the simplex is a LVA. Lipschitz LVA is mean I define here. It's just linear vertex approaching. So that's LVA map. Is LVA map from sigma from delta n hat to x 0 to x 0. So know that. So we have the phase map, right, for nk from n minus 1 to delta n. Is mean take delta n minus 1 to a phase of delta n. Is defined as usual like b0 or bn minus 1. So we go here, we take that is b0, bk minus 1, 0, bk, bn minus 1. So we have this map. And this map induced, we can define the same map, similar maps in the case of delta n minus hat to delta n hat by define t x here. And so we go to do the same. So I take t ink of x and t. So it means it's take a phase takes delta n minus 1 hat to the phase of delta n. So we also have the can define the boundary map sigma as usual. I just take minus 1k of sigma j. This is jk, okay, jk, ik, sorry, ik and hat of sigma. This one, okay. K equals 0 to n. We have the boundary map, and then the complex. We have the complex. So I denote that MD C of x0. Of course, we have dx and a AGEA abelian group. That's we take the O's of the change sigma I, AI's belong to A. That's usual. So here, because I put here pre, it means we are not using this yes. So we have to define some relation we call immediate relation. So immediate relation. So I take given two change z1 equals sigma aj, right? Sigma j belong to j, and z2 from bk sigma k belong to k, two chain in this one, in this complex. So I write z1 immediate to z2 if there exists a subdivision. So for each I, so I have the subdivision sigma ij delta n to delta n. What is subdivision? I mean, so here we have an x. This is x. So we have the this is delta n hat. Okay, so here we have delta sigma j. So subdivision is mean we have to triangulate the delta n. So for each the big good box here is this is delta n. So we have here a map over here. So this map is I call sigma ij. Okay, so this is equal to this. Yeah. So subdivision like this, so that we take the sum of after subdivision. So ij we take also the sign, the orientation of this sigma ij. I belong to A, J, and J belong to J. Is exactly sigma bk sigma k belong to k. Yep. So if we have after taking division, we have the sum exactly the sum of z2. So we have the notion z1 immediate to z2. So then we can define the equivalent relation. So I can say that z1 equivalent to z2 if there exists and z, so we have the z1 take subdivision up to after a certain step we get z here, and we also get z2 take subdivision. So after certain step, so we get z here. So then we have definition, and then now we are ready to define the MD homology, at least for b equal infinity. So then we have the new complex that is MD C infinity of x x0. Let me just omit the notion of a matrix, and the abelian group actually equal MD homology pre and divide to this relation. So, and then with the notion of a boundary map, we get the notion of MD homology of x0. So we get the notion. But here we haven't seen any Lipschitz involved here, right? So now I studify that is given speed b belongs to from 0 infinity. So I'm going to define what it mean MD homology b of x0. So first of all, I take two simplex sigma 1 and sigma 2. That's it. And I define sigma 1 equivalent b to sigma 2 if for every curve gamma from to delta n hat. So we have the distance sigma 1 and sigma 2 divide to t power b go to 0. This means you have two curve, right? I have this one. I have the x here. So first of all, I have the here maybe yeah. I have this is sigma 1. So I have another one, rest one, for example. This is sigma 2. So if the distance between this guy is smaller than t power b with the other, so I call sigma 1 is b equivalent to sigma 2. So and then we do the similarly, so we get the notion of b immediate relation. So similar, we get the notion of sigma of z1 equivalent to b to z2. Let's subdivide. Yeah, we just do like here. Here we take the b relation here. Yeah, now we take the relation. So then we get the notion. And then we have the new complex MD C B of x0. I define like MD C of pre-infinity. I divide to this subdivision B of, yeah, I get this one. And together with the boundary map, we get the notion of MD homology B of x0. If we get the full information, we have to put here. So the remark that, so if we take b equal infinity, this means we recover the singular homologies of the length of the set. This means MD homology of infinity here. of x0 actually equal the singular homologies of x intersect with the small sphere -1 here, and it means we do not collapse anything. And if b equal 1, and then the empty homology of 1 of x0 actually is capture the singular homology if you of the tangent cone cx0. And how about be arbitrary? So let's take a look. For example, I have a term x like this, right? And it's actually in the middle. The speed go to 0. For example, this order is 3, 5, for example, and everything is 1. So it means so after, for example, I take b bigger than 5, it means the order is bigger than 5, and the collapsing speed is not enough to change the homology of the link. It means after collapsing, I also have a little bit like this, the same thing. I did not do anything. It's bigger than 5, but if b is smaller than 5, and in the middle here, this one is collapsing. So I get my sets will be like this. It look like this. And then the homologies mean I capture the homology of the link after collapsing. So you have the feeling, right? So many interesting results were written in the paper. Here I just recall some results. For me, is interesting. Okay, so if we take 0 is smaller than 0, smaller than b2, b1 smaller than infinity. So by definition, if sigma simplex b1 equivalent to sigma prime, so imply that sigma b2 equivalent sigma prime. This is from definition. So from this, we have the homomorphisms between two groups from the complex and the homology of b1 of x and 0 a go to MDC b2 x0 a, and this induced the homomorphism between two homology. That's it. It's from MD homology b1 x. If we take x0 here, go to the MD homology b2 x x0 a. So what's mean I define the charm? The charm mean the set the number b belong to infinity, so that for B2 smaller than B, smaller than B1, B1, B2 very close to B. So we have the this map B1, B2 is not isomorphism. It's mean when B when we pass through B, so the homology group are different. It's changing. We call it a jump. So the facts that there is the first, that is jump or rational. It means only rational. The reason is because we are working with the sub-analytic. It's like Wojciech exponent, right? For sub-analytic, we have everything related to rational number. If we work with the polynomially bounded on minimal structure, so the term is not rational anymore. So it could be any real number, positive real number. The second one is the question if the term is finite or not. This means there is finitely many terms. That is what we expected, and the answer is yes. We have there are only finitely many terms. Is it okay? So, but the content of my talk is not this. So I'm continuing with the conjecture. So let me finish with the definition of MD homology. So given F between two matrix term x0 dx go to y0 dy. So which is LVA and Lipschitz. And then is induced the map from corresponding complex x0 dx to MDCB of y0 dy. And this gives us the homomorphism between two homologies. Okay, so actually, if F is by Lipschitz, sub-analytics by Lipschitz, then we can prove that F star is an isomorphism. This means the MD homology is preserved by Lipschitz homomorphism. So now we instead of considering F, we consider the identity map. Now we take the identity map from the term x0 dx. Okay, d1 go to the term x itself, but d2, two different matrices. But here I take the particular, so I take the inner, the outer. That is two usual metrics people uses usually works in Lipschitz geometry. What mean the inner matrix? So the inner matrix is inner distance from x and xy. We just divide by infimum of the length of every curve connecting x and xy and x. And the outer matrix is just the induced matrix from Euclidean matrix. So if ID x0 here is by Lipschitz, so then we call x as 0 Lipschitz normally embedded. So what's meant by Lipschitz? I recall the definition of by Lipschitz. It means that the map f is by Lipschitz if fx minus fx prime is bounded by kx minus x prime. If you take the matrix, so let's say this is dy if x from x to y, so you get dx 1 over k. Yeah, this is by Lipschitz map. So yeah, the problem, interesting problem in Lipschitz geometry, they want to answer the question is when a given set, a given term is Lipschitz normally embedded. Let I say Lipschitz normally embedded. This is interesting question. So the conjectures. So actually, by above, that is if x is 0, is if this is the question, is LNE. So it means the inner matrix and outer matrix are by Lipschitz equivalent. So I have explained above. So we get this is the identity map. Is an isomorphism. So the conjecture written in the papers say that, okay, suppose we take all the x, identity in x, that is from empty homology of x, the inner empty homology, x, the outer is isomorphism. Then we get the x, the term is L and E. So let me give some example for you to have the feeling which term is L and E, which term is not L and E. There's some example. So for example, take a curve at 0. This one is not L and E. This is not L and E. Why is it not L and E? Because we take two, for example, we take two points here. So if we go with the outer matrix, we have to go direct like this, right? If we go with the inner matrix, we have to go through the origin. We have to go in this direction. So then both distance are not a bi-Lipschitz equivalent. So the inner metric is much bigger than the outer metric, so it's not LNE. And the second example, simple example, for example, you can take I took oftenly this one. So a similar, yep. So why is not LNE in this example? So for example, we follow this curve. Suppose this curve has order smaller than order is bigger than 1, for example. Order here is 2, for example. So we take 2 points here, a point here and the point here, right? And the inner matrix and the outer matrix, we have to go in this direction. And for the inner matrix, maybe we not go through the origin, but we have to go around, right? Something we have to go around like this, and it's easy to check that the inner metric and outer metric are also not bi-Lipschitz equivalent. However, if we take this one, yeah, this one is LNE. Why is this one is LNE? So we can see that if we take 1 point here and 1 point here, we go with the outer metric, we have to go direct from here to here. But we go with the inner metric, we have to go through, I mean, around the circle. But the length of the circle and its diagram are almost similar, right? So this is LNE. Okay. I'm going back to the conjecture. The answer is no. It's been in general. So I give the example. So I take x equals x z t belong to R3. So that z square equal t square x square, and I take x is bigger than 0, smaller than t. So if you look at this, the picture of this example is look like this. So I have the coordinates in R3. I get the x in z-axis and t-axis here, and the set is look like this. Yeah, this is the term of x. And the facts is the first one is if for every x we have the identity map x actually from MD homology B of x 0 the inner to the same one. Sorry, the out that is isomorphic for every x inside the germ near 0. And the second one is x, this germ is not LNE. So how to prove it? So actually I give a simple proof. So first of all, I check 1. So there are 2 cases. X is different from 0. So we easy to see that if x is different from the origin, so we have in the neighborhood of x, we get then x is a Lipschitz regular point. It means there's a neighborhood u of x in x, so that u is by Lipschitz equivalent to a ball, I mean the B2, as is by Lipschitz. or uh, in another words, that is x, and the term of x as small x is L&E, Lipschitz normally embedded, because it's by Lipschitz with a ball. Ball is Lipschitz normally embedded. So this implies that, of course, the induced homomorphism is an isomorphism. And we only check with x is equal 0. So in this, I take the Lipschitz retraction. Take the map x from x cross 0, 1 to x. So I take here x, z, t, and here s, for example. I put this here sx, sz, t. So actually this map is, we have h0 actually equal identity, and I take g equal x0. Actually this is a map from x to y equal y axis, z axis. This map is, yeah, it means you are moving, yes, you are moving first with s, so you're moving from this to this. You retract x to this t axis, so it just retracted smaller. And this map is Lipschitz because we have h. Sorry. Easy to prove that hs is Lipschitz for every s, and the Lipschitz constant independent of s, do not depend on s. And by a theorem in the paper, so we get that the map from MD homology x0 and d to MD homology x0 and y0 and the actual this homology is isomorphic with the isomorphic with the homomorphism induced by the identity map. It means the x0 here and the x1 induce the same homomorphisms. So actually this one is isomorphism with d for both. That is, d can be the inner matrix or the outer matrix. So then we have the commutative diagram. So MD homology of x0 and the inner. Go to here to MD homology x0 the outer. And here we have the no, this is y, sorry. And this we have the identity map at 0. We get MD homology of x0 d out and MD homology y, sorry, the in to the in, and this is the out. So we have identity. So what do we have now? So we have now here is isomorphism, and because you see y is a half line, right? Y is a half t axis. We have y actually equal like this. This one is L&E because the inner matrix and outer matrix in this term are the same. So we get this one is also isomorphism. So because this diagram is commutative, so finally we get this one is isomorphism. And we finished proving the isomorphism as the origin. So now I want to check that how to see that X is not only. So we use a theorem recently established by Sambio and Mendes. They show that if X, the term is connected, so X is Lipschitz normally embedded, if only if we can check it through the link. It means X intersect with the sphere is A1E and the A1E constant do not depend on the choice of epsilon. It's been if you want to check the A1E of the term, so you just only check the A1E of the link, so and check the Lipschitz the A1E is constant. So actually remarks that instead of this, we can check with the general link. This means we can replace the link, right, with general link. Is mean I take X, I take the intersect with the inverse, the fiber of some Lipschitz map, and sigma is actually from X to, so that this is Lipschitz. And sigma X is equivalent to X. So what does it mean here? This mean, by this I mean that there is an K bigger than or equal 1, so that this one smaller than X K and bigger than 1 over K X. So now I back to the example. I take a rho actually equal the projection. Rho equal the projection from R3 or from X to R, Y, and I go to T. So let me draw the picture again. This is T. So this is the set X, right? So actually, if you take a rho, actually, this is the projection. So then we have rho minus 1 of T intersect to X. Actually, has this form. It's like the V. But the angle here, let's say alpha T. So actually, the Lipschitz, this one is A1E with Lipschitz with A1E constant 10 to infinity, because when we take 2 points in 2 different branches, we want to go from one point to another. So by inner metric, we have to pass through the origin, but the angle is smaller. It means the distance will become bigger and bigger. So then, because the only constant here is not uniformly bounded, so this is given the x0 is not only. So I finished the proof. Actually, this is very simple example. through the counterexam, to the conjecture of the paper. So some remarks. Actually, this theorem, I have a result saying that this theorem actually is not only true. This theorem is not only true for semi-algebraic, it's also true for any definable term in our minimal structure. And the second remarks that actually, you see my example is this with a non-isolated singularity. So it's mean the conjecture so still open for the isolated singularity case. So especially I think if it's not true, so it's likely true for the complex case. I don't see any reason it's not true for non-complex case. For complex case is very special. And because I have a couple of minutes, so I want to tell you some new result about MD homology. I hope this the paper will be on ASCII soon. It's not really related to my talk, but it's so very, because MD homology is a new theory, right? So actually, it's very hard to calculate the MD homology. Even in the case of singular homology, right? Calculation by definition very difficult. And then usually we have to use the cells homology. In a singular homology, we use cell homology to calculate the singular homology. And then with MD homology, so recently we developed something similar to also have the self MD homology. We can calculate this. And what does it mean? I mean, cell MD homology. It means it's like this. Given a very strange subanalytic term, so we will show that there's a biologist homomorphism H. We make it into kind of cell decomposition. Very nice decomposition. It's like this. And it has some information. Maybe yeah, it's like this. Yeah, I don't know. Maybe here. And we have some, okay, something like this. And with some number here, right? I have some data here. So this is combined natural data. And from this combinatory data, I will tell you exactly what is MD homology. Homology P of x0 with the alter matrix. It means you just give me B. I will tell you what is exactly the MD homology, because this is biology. So yeah, actually we can do that. Okay, so I think I will stop here. Thank you very much.
Yeah, thank you. Very interesting talk. So we have time for some Comments, questions? So how is the comparison with of this cohomology with the singular cohomology? Any maths?
Actually, it's more stronger. You've seen that is the homology. If I take D equal infinity, actually is recover the singular homology. Actually, because why we're talking about the link, because we are talking about the term. The topology of the term is determined by topology of the link, right? It's reasonable to talking about the link. And when you take B, you let B move from infinity to 0. This means your space will collapse, smaller, smaller, or whatever. And then you keep tracking, and then you want to see when the homology change, when and actually from this picture, from this data, actually is reproof the theorem I told you before, that is the number of term is finite because I have the combinatoric, and also we have the what I told before, that is we also can prove that the term is rational because the number here is rational. So but actually this one is a Lipschitz invariant, but it's not that strong to tackle the Lipschitz type. It's like you have the homology is topological invariant, but it's not enough to say about the topological type, right? It's also just invariant, but I think it's useful. Yeah. It may have more application, especially in physics.
I see. Yeah. Okay, so if no comments or questions, so let's thanks Nhan for a very nice talk. So
Okay.
okay, so